So, in this session we will start about the discussion pertaining to this irreversible series reaction. Again, it is the same batch reactor kinetics. So, irreversible reaction in series. A giving R giving S. So, K1 and K2 are the rate constants. So, you can see that minus of dCA dt is equal to K1 Ca, which gives you the integration here t equal to 0, Ca equal to Ca naught, Cr and Cs is equal to 0. So, Ca equal to Ca naught into e to the power minus K1t. So, dCr dt K1 Ca minus K2 Cr. So, dCr dt plus K2 Cr K1 Ca. So, integrating factor, it is a Leibniz differential equation, integrating factor will be e to the power K2t. So, d dt of Cr into e to the power K2t is equal to K1 into Ca naught into e to the power minus K1t into e to the power minus K2t, right. So, integration will yield e to the power K2t is equal to K1 into Ca naught e to the power minus K1t e to the power minus K2t minus 1 a plus, this is plus. So, minus 1 K2 minus K1. So, Cr is equal to K1 Ca naught e to the power, this is plus, minus K1t minus e to the power minus K2t divided by K2 minus K1. So, e to the power minus K1t minus K2 by K1. So, it is fine. Now, as it is 1 mole giving 1 mole, here also giving 1 mole. So, you can see that Ca naught plus Cr naught plus Cs naught is equal to Ca plus Cr plus Cs. So, obviously, these are 0. So, Cs is equal to Ca naught minus Ca minus Cr. So, Ca naught minus Ca naught into e to the power minus K1t minus K1 Ca naught e to the power minus K1t minus e to the power minus K2t divided by K2 minus K1. So, that can be further simplified. So, you see graphically this concentration of A decreases like following some exponential pattern. Concentration of R increases then decreases, and concentration, finally everything goes to the concentration of S. So, it will increase sigmoidally and finally saturating to Ca naught. So, this is Cs versus T, Cr versus T, Ca versus T, right. So, definitely we will be interested about the time at which the Cr reaches its maximum. So, it is a bit of algebra we have to do here. Cr we have got. So, the condition of optima dCr dt, the necessary and sufficient necessary condition, dCr dt equal to 0, K1 Ca naught minus K1 into e to the power minus K1 t plus e to the power minus K2 t into K2, right, divided by K2 minus K1. So, that is said to be equal to 0. So, you see this K1 e to the power minus K1 t is equal to K2 e to the power minus K2 t. So, this is K1 by K2 e to the power K1 minus K2 t. So, ln of K1 by K2 divided by K1 minus K2 equal to T optimum. So, that is T optimum is 1 divided by K1 K2 log mean, right. Now, if I substitute this T optimum here, you will get this CR max as CR T at T optimum, and again we have to solve a bit of algebra, and from there we can get, I am not solving it, it has been solved in the handout. From there we can get that this is Ca naught into K1 by K2 whole to the power K2 by K2 minus K1. So, you do not have to remember it, but this T optimum is pretty simple expression 1 by K1 K2 log mean. If you wish, you can remember that. Now, see, there is a variation we can have here. Let us say it is given the order is 1, right. However, 2a giving 3r and here it is 5s. Then minus of dCa dt we should write as K1Ca. Now, dCr dt we must write 3 by 2 K1Ca minus K2Cr, and dCs dt will be 5 by 3 K2Cr. So, this stoichiometric parity must be there. See, here I am not writing 2 K1Ca because it is this K1 is reference to A and the order is 1. So, it will be K1Ca. Now, for R, this K1 is reference to A, so it has to be changed. However, from R as it is dissipating to S, it should be K2Cr, right. So, these conditions of stoichiometry are to be kept in mind, otherwise you will land up solving something wrong. So, that is the series reaction, irreversible reaction in series with definitely the constant volume condition, right. Now, if it is second order or third order equation, you cannot go by this analytical technique, you have to follow numerical technique because that respective equation will be nonlinear. So, after we have solved the series, next it will be first order reversible reaction. A reversible arrow K1 K2 B. So, minus RA equal to K1 CA minus K2 CB, right. Now, you see this constant, equilibrium constant, by definition it is K1 by K2, right, and it is CRE by CAE. So CRE will be CA naught into 1 minus XAE. This will be CA naught into M plus XAE, right? So 1 minus XAE divided by M plus XAE, that is K1 by K2, which is basically K. So what you can write here, minus of dCA dt, which is CA naught into dXA dt, is equal to K1 if I take common. Here it will be CA naught into 1 minus XA minus CB. CB will be initially, let us say the concentration is 0, CA naught, or we have considered the concentration. So it is CB naught minus CA naught XA plus, right. And divided by this will be divided by K2 by K1, so K1 by K2 here, so 1 minus XAE divided by M plus XAE. So now this CA naught we can take common, CA naught into K1, 1 minus XA, K1 by K2, and here it is K2 by K1, correct, K2 by K1. I think we are doing something wrong, we have some mistake here. CB is CB naught plus CA naught into XA, that divided by, here it was K2 divided by K1, so K1 by K2. Oh, here we have done the mistake, it will be just the opposite. So it will be this M plus XAE 1 minus XAE. So this will be CA naught we are taking common, so M plus XA divided by M plus XAE, and here it will be multiplied by 1 minus XAE. So it is K1 CA naught 1 minus XA into M plus XAE minus M plus XA 1 minus XAE total divided by M plus XAE. So this is K1 CA naught M plus XAE minus MXA minus XAXAE minus M plus MXAE minus XA plus XAXAE divided by M plus XAE. So XAXAE plus this cancels out, right, M and this M also cancels out. So XAE and here M plus XAE. So what you can write, KCA naught into this XAE minus XA 1, this and this, and here minus M minus M. So minus M if you take common, XA minus, or rather plus M if you take common, XAE minus XA. divided by m plus xae, which it will give you xae minus xa into 1 plus m divided by m plus xae into k1 Ca naught. So that is simply integrated. Now Ca naught and this Ca naught cancels out. So we have dxa divided by xae minus xa, and on this side we have 1 plus m plus xae into k1 into t, and this is to be integrated from 0 to xa. Right. So minus of ln xae minus xa plus ln xae is equal to m plus 1 m plus xae into k1t. So it is minus of ln 1 minus xa by xae m plus 1 m plus xae k1t. So here you can understand that if I plot this minus of ln 1 minus xa by xae versus t, I must get a straight line with a slope of m plus 1 m plus xae into k1, and we can solve for k1 from here. Yeah. Now regarding this is all about the integral method of analysis for constant volume. Now if we go for differential analysis, what may happen? Just let's have some very basic idea. You see, yeah, differential analysis, again constant volume. So generate Ca versus T data set, right, at a constant temperature. Evaluate minus Ra, which is equal to minus of dCA dt by numerical differentiation. So last is solve for minus Ra as a function of Ca. Now here you see, if minus Ra is equal to some kCa to the power n, go for log plot, as log of minus Ra is equal to log of k plus n log of Ca. So you are plotting this and this. This is y axis, this is the x axis. So the slope is equal to the order, intercept is ln k, right? But you can have something which may be different from this form, that is 1 divided by minus Ra, or minus Ra. This is the typical Michaelis-Menten kinetics. K1 Ca divided by 1 plus K2 Ca. If this is the form, definitely this will not work here. So what we have to go for? 1 divided by minus Ra equal to 1 plus K2 Ca divided by K1 Ca is K2 by K1, that is the intercept, and 1 by K1, that is the slope, into 1 by Ca. So here we will go for a plot of 1 by minus Ra versus 1 by Ca. So the intercept is K2 by K1, the slope is 1 by K1. So we can solve for K1 and K2 from this sort of analysis, right. So you have to think about the equation, and from there we can find out actually the slope. So next, it's a topic of constant pressure or variable volume reaction. Now you see, most of the gas phase reactions are variable volume. Liquid reactions, if it is mentioned not constant volume, but if it is stated both are in liquid, both the reactants are liquid, so liquid reactions are constant volume reaction. Right. Now here the volume changes with conversion. So we'll write that V is equal to V naught. This is the initial volume when conversion was equal to 0 into 1 plus epsilon A xA. Right. So basically delta V what we are talking about is V naught into epsilon A xA. So epsilon A must be delta V from xA equal to 0 to xA equal to 1 divided by V naught. From here it is obvious, because xA equal to 1 if I set, then delta V, full change in volume from the full conversion, that is, we can define it as a fractional change of volume for full conversion of limiting or target reactant. Right. So discuss about how to solve for this epsilon A, knowing the stoichiometry and initial composition of a system. See, let us say a reaction 2A plus 3B giving 5C plus 7D. Right. A was equal to 5 mole, say at xA equal to 0. It is given. A is equal to 5 mole, B is equal to say 10 mole, C is 1 mole, this is 1 mole, and 5 mole inert is present. Right. So xA equal to 1, what will happen? This will be 0, this will be 0 mole, and this will be 10 minus 3 by 2 into 5, because from 2 moles of A, 3 moles of B react. So if 5 moles of B is reacted, then how much amount of B will react? So it will be 3 divided by 2 into 5, right, that is 7.5. So what will be the amount of C that is formed? 1 plus 5 divided by 2 into 5. D 1 plus 7 divided by 2 into 5, and inert remains 5 moles. So if you add this 20 and 22, so N0 is 22, N xA equal to 1 we can calculate from here, right, and we use Avogadro hypothesis that number of moles is proportional to volume, right? So epsilon A is equal to n at xa equal to 1 minus n at xa equal to 0 divided by n at xa equal to 0, and from there we can solve, right? That is the understanding of epsilon A. So with that idea of epsilon A, let's first write what will be minus Ra. That is minus of 1 by V dNA dt. Now Na, you see, it's Na naught into 1 minus Xa, and V, which is no longer a constant, epsilon A Xa. So let's substitute it. So dNA is equal to minus of Na0 dxa. So here Na0 dxa dt, and here V0 1 plus epsilon A xa. So Na0 by V0, that is equal to Ca0 or Ca0 divided by 1 plus epsilon A xa dxa dt. Right. So that will be the rate expression. Previously it was simply Ca0 into dxa dt for constant volume system. Now let's go for zero order variable volume reaction. Now here you see we are measuring the volume, and from the volume actually we have to relate or generate the conversion data, that is Xa. So what we can do? Zero order minus of Ra is equal to K. So this is Ca0 divided by 1 plus epsilon A Xa is equal to, into dxa dt is equal to K. So Ca0 by epsilon A ln of 1 plus epsilon A Xa equal to K into T after integration. So you can write this as Ca0 divided by epsilon A ln of V by V0 equal to K into T. So you see that instead of noting or finding the conversion, if we directly calculate V, we can actually solve for this K. So what is to be done? We will simply plot ln of V by V0 versus T. So the slope will be K into epsilon A divided by Ca0. So you know epsilon, you know Ca0, so you get the value of K. Right? Second, it's a first order reaction. So it is minus of Ra, which is Ca0 divided by 1 plus epsilon A Xa into dxa dt equal to K1 into Ca. Now this Ca, now how we can write it? K1 Na, which is Na0 into 1 minus Xa, and V, which is V0 into 1 plus epsilon A Xa. Right. So this becomes K1 into Ca0 into 1 minus Xa divided by 1 plus epsilon A Xa, and which is this. So this and this cancels out, Ca0 cancels out. So we are getting the same equation as that of constant volume systems, which is ln of 1 minus Xa equal to K into T. Now say we don't want to calculate this Xa separately, we want to directly fix it up from the change in volume. So that can be easily done. So V minus V0 equal to 1 plus epsilon A Xa. So V by V0 minus 1 whole bracket 1 by epsilon A, which is delta V, because V minus V naught is delta V, right. So, delta V divided by V naught into epsilon A, that is equal to Xa. So, we will substitute it here, 1 minus delta V by V naught into epsilon A is equal to K into T. Now, you see we have collected T versus V. So, from there we can calculate delta V, which is 0, which is V minus V 0, and from there simply minus of ln 1 minus delta V divided by epsilon A into V naught, and T is there. So, finally, we will plot minus of ln 1 minus delta V divided by V naught into epsilon A versus T. So, it will be a straight line passing through the origin, right, if it satisfies this first order kinetics. So, 0 order, first order, we can also think of second order, but I am not going to solve because it involves a lot of algebra. So, second order reaction. So, it is minus Ra equal to K into Ca square, right. The second order is 2A giving product. So, it is Ca naught into 1 plus epsilon A Xa dxa dt equal to K1 Ca naught square 1 minus Xa whole square 1 plus epsilon A Xa whole square. So, this and this cancels out, Ca naught cancels out. So, 1 plus epsilon A Xa divided by 1 minus Xa whole square dxa integration from 0 to Xa, this is equal to K1 into Ca naught into T. So, this is to be integrated actually. This integration finally will result in terms of volume as 1 plus epsilon A divided by delta V epsilon A V naught minus delta V plus epsilon A ln 1 minus delta V divided by V naught into epsilon A is equal to Kt. So, this entire thing you have to plot on this y axis and T on the x axis. So, the slope will give you the value of K, right. So, that is more or less about the batch reactor. Let us solve one or two problems. Yeah. Just like this 2006 GATE problem. The rate R at which an antiviral drug acts increases with its concentration in the blood C according to the equation. So, R equal to K into C, C50 plus C. C50 is the concentration, C equal to C50, at C equal to C50, R equal to 50% of this maximum rate. Now, if C is very high, you see, C is very high, so the maximum rate becomes K. Okay. You can take the derivative, and from there also you can establish that this maximum rate, and here also it is given, it is K. Often the concentration C90, when the rate is 90% of the maximum, is measured instead of C50. The rate equation in terms of C90. So, we have to write it as a function of C and C90. Now, you see, if we substitute here in this expression, put C equal to C90 and R is equal to 0.9 K. Right. So, 0.9 K is equal to K C90 divided by C50 plus C90. Right. So, K cancels out. So, 0.9 C50 plus 0.9 C90 is equal to C90. So, 0.9 C50 is equal to 0.1 C90. So, C90 or C50 is equal to 1 by 9 C90. So, you replace it simply and you get R is equal to K into C 1 by 9 C90 plus C. So, that is the answer. So, scheme is given. This is also GATE 2006 problem. 2 marks. A 1, 2, B, sorry, here it is C, this is B, this is D. The activation energies for the individual reactions, these are elementary reactions, so hence first order. Elementary reactions. So, all are first order reactions, as you can understand. E1 activation energy 100 kilojoule per mole. E2 is 150 kilojoule per mole. E3 100 kilojoule per mole, and E4 200 kilojoule per mole. So, if our feed is pure A and then desired product is C, C is the desired product, pure A feed, right? Then what should be the progression of temperature such that C is maximized? Now, you can understand this is 100, this is 150. So, initially if it is pure A, so we are here. So, if I increase the temperature, the formation of C will be actually be increasing relative to that of B. Definitely some amount of B will be formed. So, we have to keep initially high temperature. But immediately we can understand that once the concentration of C is appreciable, the C will degrade to D, which has got and which is favored at high temperature because this has got a highest activation energy. So, and then low temperature then, if I have to keep the C here. So, the profile will be something like this. So, this is T max, this is T min, the allowable, with respect to time. So the options are constant at low temperature, constant at high temperature, increasing and decreasing. So you must be decreasing the temperature. Yeah, next. This is a series reaction A to B, B to C, K1, K2, right? This is first order, this is 0 order. Feed concentration Ca0 is 1 mole per liter. The time at which concentration of B will reach its maximum value is given by. So, minus dCA dt equal to K1 Ca. So, Ca equal to C0 Ca0 into e to the power K1T. Now, dCr dt is equal to K1 Ca minus K2, right? K1 Ca minus K2. So, this is K1 into Ca0 into e to the power minus K1T minus K2. So, that is dCr dt. So, simply what you can do here, this must be equal to 0, right. So, if it is equal to 0, K1 into Ca0 into e to the power minus K1T equal to K2. So, this yeah, Ca0 Ca0 must be there, I think. Because the units are not identical. So, e to the power minus K1T is equal to K2 by K1 into Ca0, right. So, minus of K1T equal to ln K2 by K1 Ca0, that is K1T is equal to ln K1 Ca0 by K2. So, T is equal to 1 by K1 ln of K1 Ca0 by K2, right. The time at which B will reach its maximum. The time at which concentration of B will be 0, right, concentration of B is 0. So, you see this is the fall of A, this is the rise, and next it will fall like this, and S will grow or C will grow. So, the question is when the concentration of R is 0. So, you have to solve this dCr dt or this is the maxima, fine. So, Cr from here, Cr is equal to minus of K1 Ca0 or e to the power minus K1T by K1 minus K2T, right, and this will be from 0 to T. So, there will be an exponential, and here you have to set Cr equal to 0 and solve for T. Yeah. Next, the liquid phase reaction. This is 2008 problem. Liquid phase, immediately we have to conclude that epsilon A is 0 or constant volume system. A gives product governed by the reaction minus Ra is equal to K into Ca to the power half. If the reaction undergoes 75% conversion of A, so Xa is equal to 0.75 at T is equal to 10 minutes. In an isothermal batch reactor, the time in minute for complete conversion of A. So Xa equal to 1 at T what? That we have to solve for. So minus of dCA dt equal to K into Ca to the power half. So minus of Ca to the power minus half dCA integration from Ca naught to Ca is equal to K into T. Right. So Ca naught Ca to the power half divided by half Ca naught to Ca equal to K into T. Right. There is a minus sign as well. So 2 into Ca naught half minus Ca half K into T. So that's the equation. So Ca 75%. So Ca will be equal to Ca naught into 1 minus 0.75 and T is equal to 10 minutes. So you can solve for K as a function of Ca. And next, once you have got the value of K, you substitute Ca is equal to 0, and from there, so once you have got K, next set Ca equal to 0 and knowing K, solve for the time. Right. Next, the half life of a fast order reaction is 30 seconds. What is the time constant in minute? So it will be log 2 divided by K. So you can solve it out, but not from that equation of T half what we have derived. Here we have to use the first order because there to the power Ca naught to the power n minus 1 was there, right. So you can do it directly, and the denominator there was an n minus 1. So you can do it directly like ln of Ca naught by Ca is equal to K1 into T. So Ca is equal to Ca naught by 2 and T is equal to T half. So ln of 2 is equal to K into T half. So K is equal to ln of 2 by T half. So that's all. So that's all about the batch reactor data's interpretation, right, and some of the example problems we have solved. So in the next class, or next session rather, we'll go for design and solving problems of these ideal flow reactors. Thank you.